Welcome to Breadboarding. Continuing the Nanocomp series of videos, this is first in the series of adding a video controller or video card to the Nanocomp computer, which has been built on breadboards. So first of all, why should we try and build a video controller on breadboard? Well, in my introduction video some time ago, there's much discussion about you should only use breadboards for low frequency circuits, you can't use them for high frequencies. Now, what I hope to prove here is that you can quite successfully build projects that work at frequencies higher than 10 megahertz. In fact, in this particular case, we're starting with a 25 megahertz dot clock, which is the base VGA. And in fact, what I'll try and do in later videos is see if we can stretch that to 40 megahertz and see if we can even get super VGA resolutions. VGA is normally considered to be 640 by 480. Super VGA starting resolution is 800 by 600. What I'm trying to do here is use 1980s and early 90s hardware. So by far the easiest thing to do would just be to get a Raspberry Pi or an FPGA and to get a design and generate VGA signals coming out of one of those. But what I wanted to do is stay true to the original 1981 design of the Nanocomp and try and use chips from that era wherever possible. In particular, chips that can easily plug into breadboards without needing additional sockets and adapters and things like that. I also wanted to make the best video controller possible with the Motorola 6809. And in particular, having had a Dragon 32 computer, which was a 6809 based computer, very similar to the Tandy color computer back in the 80s, I wanted to try and recreate the capabilities that the Dragon 32 had as I would have liked it. The video card on the Dragon 32 was a little bit more limited than the one that we'll be using here. It's going to be VGA compatible output. That doesn't mean to say this will be a VGA compatible card. It wouldn't necessarily run software on an 8086, but it will be capable of producing similar resolutions and similar electrical output. We're hoping to use this to understand how video controllers work and how the video signals work. It would be interesting to see if we could stretch this to super VGA, so that's 800 by 600, which certainly I would expect perhaps be beyond the limit of a breadboard, but it'd be interesting to see. So how are we going to do that? Well, I'm going to use the Motorola 6845 CRTC compatible chips. So in particular, I'm not using the Motorola version of the chip. There's an Hitachi 46505, which is pin for pin compatible, very similar. I'm going to be also using a dual port RAM. Now, what that is the RAM that actually has two lots of address signals and two lots of data signals. That means that we don't have to have any complicated buffering and multiplexing to access the RAM. We can actually have the CPU access the RAM and the video controller to access the RAM at the same time without any problems, so you won't get any flickering or anything like that. The only downside of this RAM is they're quite big chips, they're 64 pins. They're only available in 4K sizes, which is not really quite big enough to do some of the things we want to do. We're going to be using the standard VGA dot clock, which is 25.175 megahertz. Initially, we're just going to be using a simple resistor video digital analog converter. So this is just a couple of resistors chosen of specific values to provide the necessary voltages we need to drive the video. I'm going to use a RAM character generator rather than just burning the character set into EPROM. This will allow us to play around with perhaps doing some custom graphics characters. So as I said before, it's VGA-like but not VGA compatible. So the output signals will be VGA, but the registers and the various ways how the card will operate will not be VGA compatible. In particular, I'm going to build this incrementally, building a step at a time. So I'm not just going to design the whole thing in KiCad and then try and build it. I'm going to build it out a step at a time. So this is my current plan. The step numbers and the individual line items may change, but to start with, we're going to use the basic cathode ray tube controller chip and get the vertical sync and horizontal sync and the basic video digital analog converter working. This would allow us to output a video signal to a monitor, which will at least be able to see that we're getting a stable signal and we can show some variation of colors. Then what we're going to do is to add the 4K character generator. So this is going to be 4K RAM, which will load from some character sets that we'll store in the EPROM. Because we're using the EPROM, we can default the characters to the standard set, but then we could modify perhaps the upper 128 to put some slightly more interesting graphics characters. And as part of that, we need to use a shift register, which takes the 8-bit character dots coming out of the character generator RAM and then converts them into a serial row of bits, which are clocked at the dot clock. Third stage, we're going to then add the video RAM. Initially, we're just going to do foreground and background text. We're not going to bother with having multiple foreground colors and multiple background colors. We'll try and do that with both 25 and 30 lines of 80 characters. After that, there's built-in facilities of the video chip that allow you to have a hardware cursor, and there's also other timing signals to do with blanking out the surround of the display outside of the character area. And perhaps we'll also look at then of defining a background color as opposed to just having black. Then we're going to start to extend the design a bit more. I'm going to swap out the dual ported video RAM for two very fast 32K by 8 bits chips. And this should allow us to be able to do foreground and background colors without having all the complex timing and latches that I had to do in the first version of the card that I did. It took quite a while to get all the timing of all the delays to allow the latches to get the data exactly the right time. And then this is really where it gets interesting, is to build that out to be able to do 640 by 480 pixels in 2 colors. One of the challenges of doing this with a 64K address space is that you actually need 307,000 bits to do 640 by 480 2-color graphics. And that works out at about just under 40K of RAM. So what we're going to have to do that is to start to page the video RAM in and out of the main address space. And then what I'm hoping to do, I've got some video digital analog converter chips being ordered, which should arrive in a couple of weeks. And that will allow us to have a palette of up to 262,000 colors and then choose any 256 colors out of that. So that's very similar to the original VGA spec that when IBM released the IBM PS2 series, which was the first computers to include the VGA compatible graphics. If we still have the will to live after that, I would like to then try and see whether or not we could make it configurable to work between number 5, number 6, and number 7. So that's basically covering most of the original pure VGA modes. And if we could do that, then we've effectively got something that's capable of doing most of the things that a VGA card could do. So that's the plan. I would imagine that the initial 1 or 2 of these might take a couple of videos, and then as we go forwards, this could take a little while. But hopefully we'll get a basic working video card in about 4 or 5 videos time. So why the Motorola 6845? Some of the reasons why we're using the 6845 is it was used in the Commodore PET, the BBC Micro, and the initial IBM color graphics array adapter. I would argue that some of the better graphics capabilities of the early 8-bit micros and early 16-bit micros used the 6845. It was a lot more flexible and not as constrained as there was a later chip, the 6847, that was used in the Dragon 32 and the Tandy Color. This had a lot more things built into it, but it was quite restricted in what you could do. And one of the biggest issues here is that the Dragon 32 and the Tandy only had a 16 by 32 character display and only supported uppercase characters, no lowercase. Can address up to 16K in bytes or characters with up to 32 rows. So that could address potentially up to 512 kilobytes in total if we were to maximize the address range of this. It is designed for character-based, but it can be used for graphics, as I'll be showing. The maximum frequency it's able to run at is about 3 megahertz for the character clock, and that's 25 megahertz divided by 8 is just over 3 megahertz, but the experience I've had is that it will work fine at 3.1 megahertz. Depending on the video mode you're trying to run at, the frequency and number of lines, the horizontal sync and vertical sync may need to be positive or negative. So we may need the ability to invert the horizontal sync and vertical sync signals depending on the video mode we want. And also the cursor and display enable signals quite often need to be delayed by 1 or more character clock cycles because of the way how the pipeline of the changes in the cathode ray tube controller chip cascade down through the memory and then out to the shift registers and then out to the display. So it's quite likely when we add the cursor and display enable signals, we're going to add some flip-flops and things to delay signals. We can use, when we want to access more than just characters, we want to use, for example, 320 pixels at 8 bits. We actually need to clock the address counting of going through the RAM at about 12.5 megahertz, so about 79 nanoseconds per memory access. Now, the base clock of the CRTC is not able to get anywhere close to that, but because we have to take the dot clock and divide it down by 8 to drive the character clock, we can actually take feeds off the divide by 2 and divide by 4 signals and in fact use those for the lowest memory address signals. So that effectively allows us to divide the display down into 320 character cells effectively of a single byte each, and that would allow us to do our 256 colors for each pixel, which is needed for this sort of VGA compatible color display. We're not going to use the light pen. So here's a block diagram of what we're going to have. So we've got the cathode ray tube controller chip, first of all, the 6845 compatible. We need our 25 megahertz clock. We're going to divide that down by 8, and that will give us our character clock, which is about 3.1 megahertz. And that's just within the specification of the chips here. Now, what the CRTC does is it generates the horizontal sync and vertical sync signals out through the buffers to the VGA port. These are TTL level. Whether or not we need the inverters or not gates between the horizontal sync and vertical sync signals will depend on the video mode we're trying to use. We've then got initially the character RAM that we're going to load up from the ROM in the Nanocomp initially. So we'll write some software that will load up the character RAM with character sets stored in the lower area of the main monitor ROM. But this will allow us to perhaps to change the up 128 characters. Now, what happens generally is that dot clock is used to clock shift register, and that every time the next character changes, the shift register is loaded with the new value in here. Dependent on which of the row is currently selected, you'll get the bits for each individual character line being output to the shift register, and then depending on whether the output from the shift register for a given bit is 1 or 0, it will choose whether it's a foreground or a background color. Now, to start with, the foreground and background colors we're just going to hard code on the board here, and in later phases what we'll be doing is loading the foreground and background colors from some memory somewhere. But in this first design, we're just going to be dealing with the video RAM doing the characters and the character RAM just doing the bits of the character display. The CRTC initially is going to be doing up to 30 rows times 80 columns. Now, this is slightly more than 2K. There are some other symbols I've got here. These will be added into here at different points in time. When we add the cursor support and when we need to add display enable and things like that, we will be needing some delays to put in here. So I've just put these on here at the moment. It's a relatively simple design initially. Depending on how things work with the color display, we may or may not need to add some latches in here. I'd like to try and do this without latches because it makes things much simpler from a timing point of view. There are some challenges in doing this, but the experience I've had has indicated that at 25 megahertz we should be able to build quite a stable display. What I'm going to show you now is the original board that I built and the output. So what I have here is the original video card that I built for my first version of the Nanocomp, and this is running a number of test programs. This is the first test program, which is using almost 29 to 30 lines on the screen and 80 characters across. You can see we have the character set here and some of the colors down here. I have to say that the video camera's getting a little bit oversaturated. The screen doesn't look as bright as it does when looking at it with your own eyes. The camera's a little bit too much brightness here. And this is the document camera, which is just orientated to look at the display, just to see as a comparison, to see how well things look. It does look a lot clearer, not quite as oversaturated as some of the webcams are. Okay, so this is actually the video capture device. So this is a VGA to HDMI converter, then going into an HDMI capture card, then plugged into the computer. It looks like it's a little bit shifted over the right hand side, so we're starting at 1 here and only getting up to about 75 on the screen. I'm just going to try loading some of the other programs to see if it works at some of the other resolutions better. So that was with number 4. Now let's try number 1. Number 1. Okay, so that is a little different. And now we'll try number 2. This is number 2. They do actually appear to have virtually the whole of the display there. That's good. Then we're going to try number 3. This is number 3. This is shifted over a little. See that we've... So, in fact, of all these ones, then number 2 was actually coming out, I think, better to where we started. We'll try number 4 again. The advantage of the PRTC controllers is, though, that you can vary these parameters and move the display around. You don't have to change the hardware, you just have to change software configuration registers. So it does make it a lot more flexible. This is the same. So in actual fact, to get our 80 characters on here is actually CRT2 seemed best. Okay, so this is my original version of Nanocomp. You can see the layout slightly different in that in the version I've included in these videos, I included the chips actually in the middle here, so it reduced the length of some of the bus wires and things. We have the processor over on the left hand side here, buffers, peripheral interface adapter over here. Then we have my original display and an earlier version of the keyboard. You can also see at the top here, I've actually got the full power blocks up there with some 8mm plugs going in the back, but that did tend to be a little bit bulky and stuck out the back of it too much. The more recent design, I've actually split these bus rails into 2, and so we only need 1 block to drive the whole board. But you can see here that I've got power rails coming round to my connectors here, another one to here, and another one all the way around to here. Now this board down the bottom here is where the video card is, so we'll just move this. This is the video card part of the circuit. What we've got here is the CRTC chip, so this is the equivalent of the 6845. Actually a Hitachi device which is compatible. I've actually got the video RAM here, so this is dual port video RAM, so it is able to connect the data and the address bus on both sides of the chip. And on the CPU side, then this is where the CPU reads and writes the data to the memory here, and then you can see here that the video chip is actually driving the address lines of this as well. Over here, we've actually used in this particular design, this is an EPROM for the character RAM. In the new design, you're going to use character RAM because it's a bit more flexible, but this has the character set hard coded into it. Over here is where we have the clock circuit, so we've got a 25.175 megahertz crystal here with the various shift registers and counters here for dividing down the values, various bits of logic, and we've got quite a few flip-flops down here that we need to delay the signals that come out of the CRTC here. And then down here, this is where we have a number of registers where we have a pipeline so that we take the color and the character position out of subsequent bytes, and we then store one for the next character in these registers here. And you can sort of see the colors here indicate which colors are being connected up to things, and then basically depending on whether or not you've got a background or foreground color, there is a selection signal on this chip here that says if you've got a 1 coming out of the character generator here, then it will choose the foreground color. If it's a 0, then it will choose the background color. So basically this allows us to have 1 byte for the character and 1 byte for the foreground color and the background color. And then we have some buffers here that are used to drive the video connector here. And this is a nice little Gravitech VGA adapter. This allows us to have the subminiature D connector, the 15-pin subminiature D connector, to 15 pins just plugged directly into the breadboard. So this is the original design. What I've learned from this is we probably need to have a little bit more careful about where all the high frequency signals are. There are a number of high frequency signals coming down to the bottom here. You can see from the earlier videos that this does work. It's quite a stable display, and the accepted practice that you can't run breadboards at more than about 10 megahertz doesn't appear to be strictly correct with the higher quality breadboards that we're using here. This is the first version of the board that I created, and the reason why I'm sort of making videos of this is because I'm going to start to dismantle this, because there are certain things. I only have one of these connectors, for example, so I am going to have to start dismantling this. In the next video, what we'll be doing is starting to build out the video digital to analog converter and wiring up the 6845 cathode ray tube controller to be able to produce the basic horizontal and vertical sync signals, so we can start to drive a monitor in the first video. I hope you found it interesting. If you don't want to miss out on future videos, please hit subscribe. And if you also found it interesting, please hit like as well. It just helps to make the video available to a wider audience. Thanks for watching.